Keep everyone on.
And you did go to the. What is it? And that's what it is.
Sorry to the Zoom folks, I just kicked off. Should just be able to join again. Okay, let's start here. A couple of announcements. I can't do office hours today, so there won't be office hours, but probably more importantly is I posted last year's midterm up here on Piazza. So yeah, we did it like mid-April. The last time when you did it, and it's timed to be 75 minutes because I think this class is only technically 75 minutes. So do show up on time. We grade all these in Gradescope, so I'll load all them into Gradescope. You know, I'm not going to go through each and every one of these. I will post the solutions to this in about a week, but I want you to take a look at it, you know, and try it yourself before you just go look at the solutions. It'll be a mix. It'll be a similar sort of content breakdown. This one had 3 larger questions. First part was really just about CUDA basics, like do you understand what's going on with CUDA programs? Questions of divergence around memory accesses. What else do we have in here? So again, this is just about like sizing thread blocks differently and trying to think about how memory transactions are affected by the size of the thread blocks. So like sort of, if I give you a piece of code, can you understand that piece of code and understand how the GPU specific parts of it interact with the system? Okay, so I didn't ask you to write CUDA code, and I won't ask you to write any big chunk of CUDA code during this exam, but I do expect you to kind of understand how this works. Then we had a more detailed CUDA example, so sort of more, this is a real piece of code. This was like a piece of code taken from sparse matrix multiply kernel. It required some thinking, right? We gave you a pictorial diagram of what the code did, and then a description of the code itself, and then ask some questions on, you know, what happens with the efficiency in such a code when there's input dependence. This took a bit more. The first part is sort of like, okay, do you basically understand how CUDA works? And the second part is, do you understand a program that's a little bit more complex? So it took a little bit of sitting and thinking and looking at the problem. Same thing with that part. And then there was hardware. So the first 2 questions were on CUDA. Don't expect that there'll be 2 questions on CUDA, but 2 questions on hardware. You know, the breakdown of points here is like roughly, it's like 42% hardware, 68% CUDA, or 58% CUDA. And then I asked some questions here on operand collectors. So we went through an example of this in class. They had a detailed sort of like step through what happens on each cycle example. I may not ask you about operand collectors, but I may, right? Or some other mechanism that we talked about in class. You know, any of those mechanisms can kind of be fair game to test. And then some questions about the SIMT stack. So again, the piece of hardware, talking about reconvergence PCs, seeing if you understand what's happening with that stack as a piece of flows, and then a little bit on the memory system. In this exam, I asked you about physical mapping in the memory system. So you had to have an understanding of like how many bits were associated with each thing and how you would stride the bits to try to maximize entropy in certain places and avoid conflicts. And all that we talked about on memory system mapping was sort of tested in these questions. So these are concrete, excuse me, these are concrete examples of questions I could ask related to the hardware and software stuff. You may get some overlap, you may not, right? It may not be the same mechanism that I test, but it'll be fair game. The complexity will be about the same complexity as this. And you know, maybe it'll be a little bit shorter. Maybe this exam was a little long. I have to go back and take a look at how things went. I don't try to time it so you run out of time. I try to time it so you have enough time. You know, if you sort of prepared sufficiently. If you didn't prepare, then you always run out of time, right? Because you just don't know what to do. But that's kind of my goal. And the goal is to have like a fair, but not super easy exam, right? I need to test you to see if you actually understood the material. I'm not here to like create a bell curve and, you know, try and figure out who's the top 5%. That's not really the goal. The goal is just to test that you understand the material, force you to study it, force you to create a study sheet. Hopefully that sticks in your mind more in 5 years when you go back and think about this class. Any questions about the exam, old exam, content of the exam? And nothing here on the DNN specific accelerator stuff, and I won't do that again this year. It'll just be CUDA and the GPU hardware. The stuff we're doing now is more like, you know, trying to give you an appreciation of other types of accelerators, but I'm not going to test you on this on the midterm. This is practically a final, right? It's like basically at the end, but I'm not testing you on the last bit of material. Plus, we don't have to come in on finals week because it's in the last week of class. Questions? Okay, good. I will put, like I said, I'll post the solutions, but not right away without the solutions. See like where your misunderstandings lie. Let's go back to this thing. Okay, so we finished off last lecture talking about this taxonomy, okay, of different data flows. So we said, all right, GPUs are one thing, SIMD engines, they're shuffling everything in and out of the register file. You can write tiled optimized code for these things. How do all of, you know, a lot of these machine learning accelerators, how do they outperform GPUs, right? That's sort of the game. The GPU is the gold standard. There's a bazillion papers on trying to propose specific accelerators for DNNs. How do they do it? And we sort of went through the fact that data flow is one of the main mechanisms. Okay, they don't use a register file that everyone has to communicate through. They will chain together processing elements, share data among those processing elements. But then the challenge becomes, how do I map all of the different parts of my deep neural network into these processing elements? And GPUs is kind of easy, right? Everything goes into, things go into shared memory, things go into the register file. That's where the storage is. When I have bespoke processing elements, I need to decide what stuff stays in the processing element, what stuff goes out on the interconnect that connects them, and what stuff am I reading more globally from the buffer. And all of the different types of DNN accelerators that have been proposed, sort of, you can classify broadly into one of these three. Well, there's a fourth, which we'll get to later. But you know, these are the sort of prevailing winds on how this stuff gets mapped to processing elements. And so the bottom line is, what do we keep stationary? Okay, what is actually stationary in each processing element? We started last lecture to go over what output stationary looks like, abbreviated OS, where essentially we're keeping the partial products local to each processing element. We're flowing the activations out along the NOC inside the network that connects the PEs. So these activations aren't changing, right, as they go from one processing element to the next. It's just taking it and streaming it through. And then once you fill the pipeline, then the thing is active the whole time. And then the partial products are getting accumulated within each one. And then there's some level of weight sharing that has to occur, because now, you know, certain processing elements will need subsets of the weights that other processing elements will also need. So there needs to be some kind of broadcast network to sort of share the weights with all of the different processing elements. And again, this is not the only way of doing business. This is just one particular way that you can orchestrate your data flow network. And here, this is good because you're sort of minimizing partial sums, movement. So partial sum movement is a huge problem. Then you'd use this architecture. And when we break down all the different types, we'll sort of show that like the dimensions of the network sort of curve which way you should go, right? Certain networks will be more energy efficient if you use them with certain mapping strategies. And again, this is sort of part of the game of trying to map your particular neural nets to your particular architectures. And so we talked about a couple of examples of output stationary. One was this Shaidia Now from ISCA 15, and then this other one from the VLSI area that also sort of did this output stationary. You can sort of take output stationary and sort of classify it a little bit further. based on what output you're keeping stationary, because if you remember in a convolution layer in particular, there's multiple parts of output, right? We basically have multiple output filters. That's what the Z dimension here is. We have many output filters, and then each filter, each output activation, I'm sorry, not filter. Each output activation has dimensions if we're doing a 2D convolution. Okay, F and E, or E and F in this example. And then we have M such outputs. And this is common if you remember back to your sort of DNN decoder ring or CNN decoder ring. And then you can take these, all of these outputs that we're going to have to produce, and you can map them onto these processing elements in different ways. So if you sort of mapped single channel, so there's only one channel of the output that's being mapped here, and then we're mapping, the number of output activations with that one channel is going to be more than one. That's the sort of first diagram. If I'm mapping multiple channels, so now I have a bit of the first channel, a bit of the second channel, and so on, then that's a multiple, and both of these are very targeted towards convolutions. And then finally, if you've got fully connected layers, then you really only, you don't slide the filter across, so you don't end up with this this sort of sharing across the activation that you do when you have a convolution. So it's more like a single output element is then mapped to multiple output channels, because there's no need to sort of slide it across like you do in the convolutions. And depending on what layer you're mapping to these output stationary accelerators, you'll choose different strategies on how to partition this. Okay, so the accelerator itself, usually is programmable enough to be able to switch between these different configurations, because you don't want to build a DNN accelerator that only targets convolution layers well, for example, because every DNN will have fully connected layers as well associated with it. And most of these things also include like some bespoke elements that do like ReLU quickly, like a piece of combinational logic that is ReLU, so you don't have to have software do the ReLU operation, et cetera. And we'll see that when we see some concrete examples. So here's sort of a flow of an example of what we mean by output stationary. Again, this is hopefully pretty intuitive. If you recall back to your decoder ring, the number of output channels we have is directly proportional. It is the same as the number of input filters we have. So in this case, we have 3 input filters, each of which has 3 channels. We have an input FMAP that has 3 channels. And so that each individual filter also needs 3 channels. And then we're going to show in this example just how we sort of keep the output stationary as we move through the different elements of each of the activation and the filters. So if we're doing this multiple channel mapping, so we're going to have multiple output FMAP channels, and we're going to start to compute these partial sums. So every time weights and activations flow into the processing element, they're going to compute some part of the partial sum, and then they're just going to keep doing it cycle over cycle until it's totally accumulated and you've got the final output that you can then write out to the memory system. Because you still have to do that, right? The output can't just live in the PEs. You've got to dump it back out so somebody could read it eventually. And so in this example, we sort of start in the most logical way, right? In the upper left-hand corner of both the filters and the input activation. And then you sort of move the filter, right? This is, you're moving the filter, I'm sorry, you're taking a part of the filter. So we're not actually moving the filter here. We're just taking a part of each individual filter's so each of just a small piece of the channel is sort of coming in to do the max associated with this small part of the weights right now. And then in the next cycle, we'll do a different part of the input FMAP. So you're sort of flowing the input FMAPs into this processing array. And we're going to broadcast or read a different subset of those weights that are being broadcast to everybody. And we're going to keep the output stationary. Okay, we're going to keep it all local to the PEs. So those local registers inside the processing elements are accumulating that result that performs these dot products, these convolution operations that are happening. And we do the same thing with the rest of this particular slice. And then we've sort of got a partial product for what we want on that upper right-hand side. Then we have to move now to the next channel, right? Because like that was just one channel. So, if you basically have to do, in this sort of Tory example, we're doing like one element each time. So we did all 4 elements of the filter and then all 4 elements of a small part of the input FMAP on one particular channel. Then we have to move to the next channel because that gets aggregated into the output FMAP. And then we do that again to sort of, do the same thing then 3 times across all the 3 channels of the filters. Yes.
there enough hardware to handle multiple filters in parallel?
Yeah, so yes, usually it just depends on how big the network is and how big your DNN accelerator is. Mapping strategies here are most of the game, right? Like if you scale up the number of filters and the number and the size of those filters enough, like you can make it too big, right? And then all of a sudden now you have to tile it in a different way to try to make it work inside your accelerator. Or you have to sort of stage the computation differently. But the typical way that these things are posed in research papers is that everything fits, right? Because that's when they do best. Because as soon as you lose that locality, you're going out to some memory system and you're kind of hosed, right? So they're either tiled appropriately so it fits, or we assume that the layers and the filters just sort of fit and are able to be processed without going back and forth to main memory. Good. Other questions? Okay, so that's sort of just, hopefully this is kind of review, right? This is kind of the sanest way that you would do this if you're trying to keep one slice of the output stationary. And the way that works in this thing, right? Just sort of concretely, show you is that the blue stuff, right? The big stuff is sliding through, right? The big stuff is being fed in from this global buffer, and it's going to processing element by processing element, performing the computation. And the weights are sort of smaller, hopefully, so you can broadcast. That broadcast network is less big than the activations, and you are sort of giving each processing element the weights it needs for the activation that it needs at this time. Okay, and orchestrating that computation isn't all that hard, but you need to make sure that it's right. Now, we can take these, and we're going to see this as a theme when we go through the rest of the different types of ways we can construct DNN accelerators, and we can sort of take the core convolution and turn it into this simple loop example. And they do this in the tutorial. So let's go away from 2D convolution, because 2D convolution just makes things a little bit trickier, right? Because now everything has an X and a Y dimension, so you just end up with all of these extra loops to go over both the X and the Y. And let's just, think about 1D convolutions. It makes the loops simpler when we're thinking about how we map, the outputs, the inputs, and the weights to these DNN accelerators. So for the rest of the examples and all these little code examples, we're just doing 1D convolution. So there's basically only an X, there's no Y. So you only have to go across sort of one bounds. And you can sort of hopefully extrapolate this to 2 dimensions, but it's just way less code to show you on the screen. So if I think about a 1D convolution, it works very similar to the way a 2D convolution would work, except I only have to go in one direction instead of two. And I've got my weights here, which are relatively small. There's an R-sized weight array, that's W of size R. Then I have an input array that is I of size H. And then I have my outputs, which are going to be size E, which of course is related to, basically related to the size of the weights and the inputs and how much you're striding. Okay, that's same as when we were doing 2D, except it's hopefully simpler now. Based on doing this in 1D. So if I were to write down that flow that I showed you on the previous slide as a collection of loops, it would look something like this. Basically, I have an outer loop where I'm looping over E, which in this case is the outputs. Okay, so this is going to be output stationary. So that means that the inner loop is not moving the outputs. Okay, the inner loop is the fastest changing loop here, where I'm iterating over R, which is what? The weights. Okay, so in this example, I'm going to iterate over R, which is the weight. So on every iteration of that inner loop, R is going to change, and I is also going to change, right? Because if you look at the index for I, it's adding together the current index for E plus the R that's changing. Okay, because you're sort of moving through the inputs. You can think of it like, you start at some offset from the output, and then you iterate through the sort of, you're sort of iterating through the 3 inputs that are associated with the 3 weights you have, and then you move over, and then you iterate through the next 3 associated with the output, or associated with the weights, and so on. Okay, this is the example of the sliding window. So you can express this output stationary business as this doubly nested loop. Again, this is just in 1 dimension to simplify things. And you can notice that, of course, like there's no constraints on the loop permutations here, right? There's no loop carry dependency. It doesn't matter which loop I do first. So I can interchange those loops, okay? So if I just simply interchange those loops, would it still be output stationary? What do you think? Yes? No. If it's a flow of computation, right? That little diagram I showed you where we moved across the thing. Here you can clearly see that it's output stationary because the inner loop is not moving E. If I switch the loops, because I'm allowed to do that, because there's no dependency, then what becomes stationary? The weights, right? The weight iterator goes to the outer loop, which means that for every iteration of the inner loop, the weights aren't moving. So I can represent weight stationary as the same loop, except flipping the two loop bounds. Okay, makes sense? And this is useful because we can use this to think about the access patterns associated with all of these different ways that we can sort of map weights, inputs, and outputs to these DNNs. Okay, so this is output stationary, and we can switch things around. And if we do switch things around, then, and this is just interchanging the two loops. So now I'm iterating over R in the outer loop. So that means that for every iteration of the inner loop, the weights do not change. I still iterate through I and E now on the inner loop. So I'm sort of moving my outputs as I iterate on the inner loop. But now E is not, O of E is not stationary, right? The thing that's stationary here is actually the weights. That's what's going to stay stationary in my processing element if I were mapping these loops to a DNN accelerator. So that brings us to our next type of configuration, which is weight stationary, which is probably the most common of the three different types that I showed you. If you're doing something like PIM acceleration, this is usually what you do. You do weight stationary. Okay, you program the weights. If you're doing like a PIM, which is processing in memory, you don't really want to update it all that frequently. You want to use it for inference, meaning you don't update the weights. Then it makes a lot of sense to map the weights to the cells of the PIM array, and then that sort of represents the network. And you can sort of think of it like this is like programming the brain of the network. The weights are the brain, right? These are the things that you've trained. This is the secret sauce on why your thing works. You're programming that into the processing elements, and then you're just streaming the different inputs that you have through the thing, okay? So this is sort of maybe the most natural way to think about a mapping. Many accelerators do it this way. So here, weights are stationary, so every PE is basically responsible for one of the filter weights. The activations are now broadcast, because now if I've got a weight, right, it's going to need many different activations based on the way I'm striding through things to potentially do the accumulation, and then the partial sums are going to flow along the NOC. So the way to think about this is that we start out sort of in the beginning here, your partial sum is 0, right? And then you sort of go to the first processing element, and you're going to get that small part of the partial sum that's related with weight 0 at processing element 0, and then you're going to pass that partial result out to the next processing element, which is going to add the influence of weight 1, and then you're going to press that all the way along until you're finally done with all the weights, and then you're spewing it back out, spewing the output back out to the buffer. Okay. This is good, obviously, because it minimizes the weight energy, because the weights don't move. They always stay resident. The other nice thing about mapping this to accelerators is that now, the weights tend to be smaller than the activations, right? So if you want the whole thing to fit on your accelerator, you have a better chance of plunking the weights on there than activations. Now, look, I mean, some networks are like trillion parameter things, right? But at any given time, any given layer may not be that big. So, this is on a layer by layer basis. And then of course you have to broadcast now the activations, because now, for every partial sum, it's going to be operating on a different part of that input activation. So the network, the sort of broader network broadcasting things, the activations. Some concrete examples of this, there's an ICCB paper. This was an early paper that kept weights stationary. And again, this is a very detailed sort of cycle by cycle diagram of a particular accelerator. What's key to notice here is that the blue stuff, right, that's the input data, that's the activations that's flowing in, and then they've sort of programmed each individual fuse, multiply, add to have individual weights associated with the network, and then of course the partial sums sort of flow out the end. Another common weight stationary architecture is this thing called NVDLA. Has anybody heard of this? So NVIDIA, I think this was, 2017 timeframe, they released a specific machine learning accelerator called NVDLA, and they released all the code for it, right? The RTL is open source. If you pull this down, there's like a huge amount of documentation on like, look, this is what every signal does. Like the Verilog for this is available. Partially because like these things are pretty simple, so it's not like some pretty simple, but like still large, right? It's still like a bunch of actual code to implement this thing. But it's you can download this and play with it. Okay, so that's what MVDLA is, and I think it was a result of like an intern project that like blossomed into like this bigger thing that then they released, and they made a big stink about it because it was open source, and they're always taking heat for never open sourcing anything. I don't know in practice how many people have actually used this in commercial products, but it's out there. It is inside, or at least an iteration of it is inside their embedded parts, so the Jetson parts. Okay, the Jetson parts have like GPUs and have CPUs on them, and then they have a neural net accelerator, which is basically this thing, maybe modified a bit. And so this sort of gives you a high-level overview of what that looks like. And so again, this is very detailed because it's got the interfaces to memory sort of configured on here, and then you've got some buffers. They call this thing the convolution buffer. What this really is your global buffer, right? This is sort of the on-chip scratch pad that you're sort of flowing stuff into. Convolution core is basically just the same thing as all the other accelerators. It's a bunch of MACs, a bunch of processing elements connected together. And then they've got, some specific engines associated with the different types of layers that you might have, right? So, if you want to do, pooling, for example, that's a different operation than a matrix multiplication. If you don't have a GPU core to do the pooling operation or a CPU core, then you need some specific hardware to do that. So they've got cores on here that do pooling and sort of different normalizations, reshaping, etc. So these sort of other types of things. But the most of the compute time is spent in the convolution core, right? That's where all the max are. The rest of them are actually, relatively small fraction of the execution time. And again, they use this weight stationary thing. So this is a cartoon diagram of the way the NVDLA does the weight stationary stuff. So here they basically take different input channels and they sort of map it logically onto the rows of the MAC array. And then they take the input F maps and then sort of broadcast different input F maps to different rows of the MAC array. And then the MAC array is sort of, connected locally. It's not an everything to everything connection, right? They're sort of connecting broad rows of these things to each other. Because, if you know that you've always got something happening over a row, you don't need like everyone to talk to each other. You can just have each row talk to each other. So they sort of do it where they broadcast one particular row of the input F map to a different input channel where the weights of that particular channel are stored on one row, and then sort of compute that row, send all those partial products down to the next row that stores the next weights that reads in the next part of the input, and then it sort of flows down and you get these partial sums coming out in sort of broader chunks. And so this is, if you know that you've got things that are wide enough to be rows, and this is a more efficient way to build a processing element array because you don't need connections where you don't actually need them. And that's the way NVDLA does it. The sort of flows, so the pictorial diagram of how this works, we're going to keep the filters stationary, right? We're going to keep the weight stationary now, and so we're going to have to move basically the other elements of the computation. So the inputs are going to move. Excuse me. So the first set of MACs will take place across all of these highlighted elements, and then the next set of MACs will take place across, we'll move the you're going to move the input activation, which means you end up moving the output F map because we're using the same element of the filter because the filter stays local. And then we sort of do that thing where we're sort of exhausting all of the places where this particular square is used, right? So it's sort of like, if I look at it from the perspective of like one particular PE, I know that PE is only going to store this one weight value that's in this one upper left-hand corner. So now I have to move the rest of the stuff around this one weight, and that's what's happening. So where is this one weight read? Well, it's always read in the upper left-hand corner. So it's the first upper left-hand corner of this filter, the upper left-hand corner of this filter, the upper left-hand corner of this filter, and the upper left-hand corner of this filter. And that corresponds to these, outputs in the output F map. And of course, those are partial, right? It's not done. So then it has to send those partials down, and it's sending it to the next processing element that's dealing with the next filter element, right? So that way it sort of carries on, and you can sort of chain these things together like that. And then if your weights don't fit on the core itself, which is often the case if your network is too big, then you have to go and reload the weights, right? So you've got to reprogram that thing with new weights. And so now if I reprogram this thing with new weights, I will have a new set of weights on here, and then you basically have to cycle through and wherever that particular weight is located in the matrix. So it's not just MBPLA, there are countless examples. This is a non-exhaustive set of accelerators that use some type of weight stationary configuration. TPU does this too. Okay, tensor processing unit, this is the Google thing. They basically operate on a weight stationary as well. So it's probably the most successful commercially way to map networks, because it's kind of the simplest and the most intuitive, right? You sort of map your weights, you map the brain to the processing elements, and then you sort of flow the rest of the stuff through. Questions on this? All right, one more type of stationary. What do you think it is? What did we cover already? That's what I see. What did we cover? We covered weight stationary, that's this. What's the first thing we covered? Output stationary, what's left? Input stationary, all right, there we go. So we're gonna go to input stationary. So how does that look? Well, now the inputs stay in each place. This is kind of rough because the inputs are huge and they change, if you have funky looking layers, maybe this is okay, but it's usually, this is specific weight reasons you might want to do this. Usually if things are sparse, this might make a lot of sense. So if you look at some of the sparse accelerators that are out there, they sometimes will use this configuration. But the general idea is that we're going to flow the partial sums through, similar to what we did with the weight activations. But now we're going to, sort of send a weight to each individual input element. So there's no broadcast here on the weight, which is kind of nice. But now you kind of have this, you have this kind of large network that's sending the weights to each individual element, and then each element is then storing the input activations associated with the particular layer that you're flowing through. And again, this is not super popular because these change all the time, and it's usually easier to program the weights so that you flow through the new data instead of reprogramming the array to and basically every different input, right? This necessitates reprogramming on every input. Okay. So what are some concrete examples? So there was this paper from ISCA, I think NVIDIA was involved in this one called SCNN. This was specifically targeting sparse CNNs. So sparse meaning there's lots of zeros. It happens all the time, right? There's two primary ways. I mentioned this at the beginning of class that people are playing games architecturally to make DNNs more efficient. One is bit width. You see the bit width of things just constantly shrinking, and the other is sparsity. ReLUs naturally create a lot of sparsity in themselves when you're sort of passing from layer to layer because they're taking all the negatives and turning them into zeros. And just the way these networks are constructed, they're almost always overbuilt, right? If you've got networks with trillions of parameters, they have trillions of parameters, but you don't really know which ones are needed, right? And then after you train them, after you spend months training these on fields of GPUs, it'll figure out what ones are wanted, which ones are needed, and how that path flows. And there'll be lots of places where values are either zero or very close to zero. Because when you train this thing, it's like I need to give myself enough room in my parameter space to curve the learning to how the input looks. But then at the end, after it's fully trained, there's a lot of stuff I actually didn't need. That's what the zeros kind of represent, right? The weights ended up going all the way down to zero. Problem is I didn't know where I needed those zeros when I was training the thing. And so you end up with a lot of big networks that are sparse. And so there's sparsity in the weights, there's also sparsity in the activations. Because every time you multiply by the zero weight, right, you're gonna get another zero. And then the ReLU also makes it additionally sparse. So sparsity is kind of all over the place. And how you exploit sparsity is sort of one of the fields that is actively being looked at in both commercial systems and academically. And so this paper was sort of relatively simple way, I guess you could think of it, to accelerate these sparse matrices where you've got these zeros all over the place. And they did it essentially with indices. It's not the most elegant way to build a sparse accelerator, but you could sort of think about what's a common way to represent sparse data. Does anyone know? What's a data structure or data representation that we typically use for sparse data? What's that? Run length encoding. That's question, right? But yeah, it's similar. What's another one? Index value pairs, yeah. What about matrices in particular? Graphs also use this representation. CSR, have you ever heard of CSR? What does CSR stand for? Compressed sparse row. So basically, like, I don't want to store any zeros. I'm just going to store only good values and then store a bunch of indices that point to where those good values should be in the matrix. That's the idea. And then you lay them out as sort of these linear arrays. So you're always reading stuff. You never read any zeros. You always read either an index or a good piece of data. But now, like, the axes aren't nice and uniform, right? Because you're sort of moving across these sort of data structures in ways that aren't super predictable, like if it was dense. And so the bottom line is it boils down to having indices that sort of point to where the good data is. And this particular engine like used those indices in both the filters and in the weights. So this is a two-sided sparsity problem to try to go in and figure out where the good data was and sort of flow it through, max for that good data, send it through specific things that do ReLUs, et cetera, and then output is some sparse thing with the indices of where it should be in the sparse output. So like the colors here match the colors in the previous slides, right? So the weights, the green stuff, the inputs are the colors don't match. The weights are the blue here. I don't know why they did this. The weights are blue. And then you have, this IA RAM. So this is the stuff this is the inputs that are going to be stationary here. And then the outputs are sort of flowing out to this other buffer. And so if you looked at it, what they're doing here is actually keeping the input stationary. Now, if I go back to my loop, if you sort of remember what we were doing, right, we were sort of moving things around, right, to go from output stationary to weight stationary. Now, when I go to input stationary, I didn't have a third loop, right? Remember, the inputs were sort of dictated by both the movement of the filters and the outputs. But if I want to keep my input stationary, I can't have that I move, right, in the inner loop. So now I have to change the way that the loop is constructed. So I need something that's going to iterate. It's going to keep basically the inputs constant across iterations of the inner loop. So if I restructure the computation, and now you get into some hairy weirdnesses where you can walk off the edges if the sizes aren't correct. So instead of just rearranging things like I did when I moved from from output to weight stationary, I'm going to change the loop bounds. So remember here, I was walking over E, which is the output in the outer loop, and then I'm walking over R, which is the weights in the inner loop. I'm going to change it such that I walk over R in the inner loop. So now I'm walking over the weights in the inner loop. And in the outer loop, I'm going to walk over the activations, and I'm going to keep the activations constant. Okay, so H is now constant inside that inner loop. And as a result, now I have to move my outputs, right? So you have to change the loop bounds to make sure that the weights or the inputs actually stay stationary here. And again, this becomes important when we start to analyze the access patterns of these things, in terms of what's happening on each cycle. Now, you have to be careful about the sizing here when you do this, because you have to make sure, that you don't end up with basically walking off the ends of the arrays. So if you rearrange, you have to make sure the sizing basically, stays within the bounds of the arrays that you have. Okay. Questions on this. So that's the sort of three basic patterns and a bunch of papers on different accelerators that have used these different patterns, some of which are commercially available, like MBDLA, for example. Okay. All right. So let's look now at the access pattern from the perspective of an individual processing element. So let's take a step back and regardless of which pattern I'm using, let's assume that I've, loaded things in, I've got registers on these things that sort of store the things I need to do in the MAC. Okay, MAC is just to multiply accumulate. So there's like a, sort of like an accumulator, right? If you've ever done ISA design, the accumulator ISA design takes the last product and then puts it back into the execution unit. And then I take in these other two things that I'm multiplying the weight and the activation, and that is the core of what the processing element does. And abstractly, they all read from some buffers somewhere, or they come from other elements when we chain them together, whatever. So let's just think about the way that these look sort of pictorially. And so if we take the output stationary and we give it some concrete values, okay, so I'm going to say that my H here is 12. So H is going to represent the number of inputs here. My R is 4, and then my R is the number of weights, and then my E is 9. Okay, so I'm giving you just concrete values so we can study an access pattern, and then I'm looking at from the perspective of 1 PE. What is happening on a cycle by cycle basis? Okay, so the x-axis in each of these graphs is a cycle of this thing that's sort of processing element that's accumulating things together. And then the y-axis is the individual elements of each of the 3 flavors. Okay, so there's 8 outputs. That means that there's 8 y values on the first graph. There are 12 inputs, so there's 12 y values on the second graph, and then there are 4 weights. So then there's 4 weight values on the third graph. Okay, and so if I look at from the perspective of a processing element, what is happening each cycle, it sort of maps out like this. And it's sort of, if I'm doing this in an output stationary way, then it's sort of clear that one cycle after the next cycle after the next cycle, the output, I'm going to basically reference the same output value in a particular processing element, right? Because it's staying in that processing element. So the output is reused many times. I'm getting a lot of locality on my output because it's staying local. And on every cycle, I'm always using that same output to perform the accumulation because I'm doing output stationary, okay? Now, what happens to the rest of the stuff? So if we look at the weights, so there are 4 weights here represented by these 4 indices, and the weights end up getting reused in this sort of, fully used pattern, right? So on the first cycle, I'm using weight 0. And then on the next cycle, I'm using weight 1. And then on the next cycle, I'm using weight 2 and then weight 3. And then I go all the way back, and then I reuse weight 0, weight 1, weight 2, weight 3, right? Is this good or bad for locality? It's not terrible in that it's not like huge distance separating things, but you are still going through the entire weight structure before you reuse it, right? So if I think about locality, like what if I just built a cache, right? Like picture I'm building a cache. Which of these things is best for cache? Of these 3, which of the things is best for caching? Output, right? Output is like, there's 1 cycle between reuse. So that means that it's definitely going to be in the cache. It's not, unless your replacement policy is most recently used or bypass, right? You're going to be able to hit on the output because it's like always in there. Which one do you think is next best? Input Y. Because the reuse distance is less, right? I mean, if in terms of sheer numbers, it's not necessarily better, right? Because there's 4 elements, right, in both. So there's this sort of repeating pattern, right, where I go through 4 elements of the weights, and then I reuse those 4 elements. So in theory, that the reuse distance is 4. The reuse distance is also 4 in the activations, but remember I had way more activations. So the pattern here with the weights is that I stride through every single weight. So as my weights scale up, this is worse and worse for locality. In this particular example, there's still just 4 in each of them, but if the weights got bigger, it would get worse. And you sort of have to stride through the whole thing. So there is locality, but it's separated essentially by the number of weights that you have, right? And then we see a similar pattern here in the output activations, except it's not all of the output activations, it's capped, okay? It's capped to what number? 4 in this case. And 4 was the number of weights, right? So the locality in the input activations is actually going to be, pretty much the same as the locality in the weights because they're proportional to each other, okay? Which is also going to be the number of times that I end up reusing the output as well. More weights, I'll just reuse that output over and over because think about it, I'm like summing it up over all of these weights repeatedly, okay? The patterns sort of remain consistent that you sort of go through. There is reuse. The reuse is separated by 4 cycles. The reuse is also separated here by, again, 4 cycles, but there's just way more of the data. So you're still getting some of the locality, but you're sort of still limited. And this pattern of like going up and then going back down and reusing the things repeatedly happens, but some of it falls off, right? Some of it, the difference between the weights and the activations is that you'll always reuse all the weights. For the activations, you're sort of, once you use element 0, you've only ever used it once, right? And then you never reuse it again. Element 1, you reuse twice. Element 2, you reuse 3 times. And then eventually you reuse all of them 4 times once the pipeline fills, okay? And then again, the pipeline drains, and once at the top, you don't reuse as much. Okay. So what we can do with these sort of analyses, like why I bother with any of this, is just try to figure out, what are the total number of reads, writes, and max associated with each of the different ways I can lay things out. So we can create like a table that sort of tells you based on the sizing, okay, where here E is the number of outputs you have, and R is the number of weights you have. It tells you how much stuff you need to read, okay? So the total number of max is going to be equal to E multiplied by R, right? The 2 loops. Okay, you basically got these 2 loops. Every time you go through one of the iterations of the inner loop, you're doing a math. Fine. Number of weight reads going to be proportional to E by R because you're basically reading the weights. If you don't have a cache, you're sort of you're reading these things E by R times. Okay, and then we can do a similar thing with the outputs. The outputs again are read E by R times because that's essentially the same pattern as the weights. The outputs are read 0 times if they're kept resident because they sort of can stay there. And then the output writes are going to be written just E times because that's how many things I have to write out, okay, to the ultimate output. So if I'm doing output stationary and I have these bounds on my loop, I can figure out what the total number of reads, writes, and operations are for this particular mapping, okay? Questions on this? Does this make sense? Now, you may ask, like, why the hell would I do this? Because we want to contrast them. We want to contrast this output stationary with a different way of doing it. So let's go back to weight stationary, right? So this was the simplest way we could reorder this loop, simply just making the weights stationary each time. And then we can map out the access patterns if we've got a weight stationary type approach. And here, we change the sizes. Don't think, we kept the sizes the same for each. So for all of these, we have to have the same size of E of inputs, weights, and activations, but the patterns are clearly a lot different, right? So if we have weight stationary, then weights are great because now weights are sort of staying in. We're reusing the weight over and over again. 12 times, 8 times. I think that's the number 8, right? Yeah. 9 times. It's proportional to the number of outputs. And then the outputs we're sort of striding through. And then the inputs, we still have the zigzag pattern, but now the zigzag pattern is wider, right? We've got a wider zigzag pattern. You're going all the way up, all the way back down. Because now you're striding over 9 instead of striding over the 4 for the weights. Okay, so it materially changes the way that these, the structure of these things. So if I take that then and then do the same analysis, max always stay the same, no matter how I map it, right? Max, like, if you map these things efficiently, the computation is just known. What you can affect architecturally is the reads, okay, is the number of times you have to go read things. The weight reads here are going to be R, okay, which is proportional to like basically going out and rereading the weights. Now, the nice thing about outputs is that I didn't have to read the first one, right? Because I know it's 0. So I didn't have to initially read it. That's not true with weights, right? If I keep the weights stationary, I need to read the weights in. I don't need to read outputs in because I know the first one's 0. So you save yourself this sort of reading in of stuff because you know implicitly with the outputs that it begins with, so you don't have a base value. For the weights, you do have a base value, so you have to read them all in if you're doing weight stationary. You only read them in once, right? You read them in, and then you can reuse them, but they still have to be read in. Input reads is going to be the same. Output reads here are going to be, instead of 0, now I have to do an E by R times, because I have to go, if I take a look at the outputs, right, in this pattern, where is it? This one, right? I have to go read, I have to basically I have to read the outputs, right? Because I have to read the output of the previous thing, right? From this global memory, or from this, buffer that I've got. So now instead of getting outputs for free, I have to read them E by R times, and output writes, I have to write them E by R times because I'm writing the intermediate result out now. I'm not just leaving it present. I have to write it out and then read it back in. So there's inefficiency in dealing with my outputs. Okay. So then we can go to the last one, which is input stationary, and then we can think about how the sort of memory access patterns work here. Here, our inputs are great because we get to reuse the inputs, but the input is, fleeting. Because 0 is only used once, so you load it once, and then you never really reuse it. And then 1 is reused 2 times, and then 2 is reused 3 times. And so you have to fill up the buffer first, fill up the pipeline first until you can reuse each element multiple times. When you get there, then you do get no reuse, but you don't get any reuse out of these other ones at the edges, or you get less and less reuse as you get to the edges. In practice, if you've got enough inputs, these edges fall off, right? Because the pipeline fills and the 2 ends of the pipeline don't really matter all that much. And your weights are going to be separated. You're still reusing them, but again, now they're separated by several cycles. Same with the outputs. You sort of have to write them back to memory at the same rate. And so the cost here, if I do input stationary, is again, max are E by R, weight reads are E by R, because I've got to read them in now every time because I'm not keeping them stationary in each element. Input reads are just E, because I don't have to read them once because I keep the inputs stationary. Output reads are going to be E by R, and output reads and output writes are both E by R, the same as weight stationary, because I still have to sort of flow the outputs through the system. So then I can say, all right, these are all the different ways I could map things. Like, what is the minimum of each one, right? So what is the best, right? If I did some mix, if I had some crazy thing that would mix things around and not just do it in these 3 ways, you can sort of take the min of each column and say that if I could do things efficiently, then I could get myself down to E by R max. Again, you can't get around it. R reads, E input reads, 0 output reads, and E output writes. This is sort of the bounds of how far you could go, right? Based on any kind of mix of these. And in this example, we what was W for again? W is the number of inputs, and we're sort of assuming that the number of inputs is pretty close to, typically pretty close to E, which is the number of outputs. They're sort of on similar scales, okay? Which is typically true. Another thing you can do is buffer. So again, this is sort of old hat for architects, right? If you've got something that is, it's better to have a hierarchy of memories instead of just one flat memory, because it's more efficient to have things as basically a cache hierarchy, for example. So I could basically have L0s, right? I could, instead of having L1 as a level 1 cache, let's put another layer lower, make it even smaller, and I can sort of cache these things. Now, the thing about adding these intermediate buffers is that now I need to worry about staying inside these intermediate buffers, which from a software perspective, what would you do to try to help keep yourself inside a small cache? What can you do to your program? Tile it. So I can take these now and I can basically tile them if I know that I have intermediate structures. So again, there are many flavors of these accelerators, some of which will do essentially this. Instead of just having one global buffer, there'll be a smaller global buffer that then they'll reorchestrate or reschedule the work such that you can stay within the smaller buffer more frequently. So this is one example of buffering things where, what did they do? Is this output stationary? They're going over E and then R. So this is weight stationary. with a, with basically wait stationary on each inner loop, right? So now you wait stationary at the L0, try to maximize locality in your L0, and then once you sort of overwhelm the size of your L0, go back out, load in another big chunk that goes to the L0, and then do it again. This is sort of a classic tiling mechanism. You'll find that tiling is probably one of the most useful things you can do in all of computer systems, because usually you end up being bound by memory, and these accelerators are no exception. Okay, so there are examples of accelerators that have these intermediate buffers, and then you basically have to make sure that you map things to tile appropriately. Sizing here, this is sort of obvious, right? Level 0 buffer is the volume needed for each of the L1 iterations, and level 1 buffer size is the volume needed to be observed to deliver the next iterations over and over. And you want to size these loop limits such that they fit inside the buffer. So the other thing about these accelerators is that they usually don't do this as caches either, because caches, why wouldn't I want to do this as a cache? What's the upside of adding these buffers as cache? Why would I want to make them caches? Versus just a buffer. What's the upside of cache versus buffer? Scratch that. Easy programming, technically adapts, right? Because what do I have in a cache that I don't have inside of Scratchpad or a FIFO buffer? Tags. I have tags. Fundamentally, I have tags. So that means I can fill that SRAM with anything I want. If it's not in there, well, go to memory and get it. Buffers are not like this. Shared memory Scratchpad and CUDA is not like this, right? It's the same thing as the shared memory Scratchpad you guys played with in CUDA. If you didn't put the right value in there, your program is wrong, right? Because it's not going to, there's no tag to check. It's just like, all right, you stored this thing in here, I'm going to give it back to you. If you didn't tile it correctly, then it's just wrong. Okay, so for these machines to try to keep them efficient, they tend to not use caches, because the caches have tag overhead, they have energy overhead, it's harder to make them higher throughput. And if everything is so regular, because I know all of the sizes before I go and like launch the program on the DNN accelerator, I don't need caches. I can just have the hardware, I can have the software basically tile things for me. As long as the software is adhering to these constraints, that you've got to make sure that everything fits inside the L0 buffer before you sort of do this inner loop, and then the L1 buffer is big enough to store a couple iterations of L0, or at least 2, right? So you can sort of feed the thing as it's processing the next inner loop. Then you're fine, and you don't need a cache. Okay. When you do tiling in CPUs in x86 programs or in C++ or whatever, like you're just relying on the fact that you have a cache underneath. This is explicit. This is saying I'm loading this stuff into the buffer. I cannot overfill the buffer, so I have to make sure that all of my loop bounds fit inside the buffers I know I have on my machine. And as a result, you can make slightly more efficient hardware, while significantly more efficient hardware, at the cost of programmability. And DNN accelerators usually opt for this because the computation is just so regular. Okay, caches are there because it's like, well, we don't really know where you're going to go. They can, general purpose CPUs and even GPUs can run any program. You got to make sure that it sort of runs sufficiently well. But if you just know exactly what's going to be accessed, there's no point in having a cache. You should just use Scratchpads. And most of these do this. Spatial processing elements. This is, instead of sort of chaining things together, we sort of have them read from they're able to basically read and then write to the buffers. We basically have a broadcast from the wait buffers and a broadcast from the input buffers, and then they can all write to the output buffers. And you can sort of lay things out spatially and, do it this way. This is another way to construct these things. Yeah, I don't know if there's much really here. So here's a summary of what I hope that you get from this whole, whatever it is, 64 slides. Ultimately, DNN accelerators boil down to essentially Mac accelerators today, right? They're essentially gem operations, convolution operations, fully connected layers, even transformers. They're just gems. So everything boils down to having a whole bunch of these Mac units, and then most of the games that are played are around data movement. We want to move data as efficiently as possible. We want to keep it in the smallest storage structure we possibly can. And then if you take a look at the last decade and a half-ish of accelerators that have used Dataflow, because Dataflow can be more efficient because there's no big register file, you can sort of classify them in these three different types: output stationary, wait stationary, and input stationary. Each of them has trade-offs on which one you'd want to use. So there's no sort of one size fits all. And, I've given you some concrete examples. And then, this kind of like loop nest thing and like visualizing how the thing moves is sort of a nice abstraction to think about what's going on inside your Dataflow accelerator, right? Some of you will maybe like work on this stuff, right? If you go out into industry, you work on the NPU unit at whatever company hires you. It probably looks something like this, and they probably do one of these, mapping mechanisms to make these things work at the low level. Questions on this before I move on? Yeah.
How many of the tiling mechanisms are handled by the pilot? All of this.
Pretty much all of them. So a lot of the work in these companies, like a company like Cerebras, I know I've mentioned that to you guys before, right? The big like wafer scale chip, a lot of the innovation is in the software tool chain. I mean, even NVIDIA's like this, right? The software stack trying to make all of these optimized libraries, map things efficiently is most of the game. So most of it's done in software, or at least as much of it as they can, because it's easier to make efficient hardware if you don't punt the complexity to the hardware. And because the granularity of the computation is so large, right? Like I know before I start processing this layer, what all its dimensions are. Why would I put complexity in the hardware to try to tile things if I can just tell the software to tile it appropriately based on, and it's going to run for like several minutes, right? And it's going to have the same access pattern over and over and over again. Then I'm going to train it over and over and over again on like batches and batches of data. The pattern is so predictable that it makes a lot more sense to put it in software than it does in hardware. So I would hazard to say that by and large, pretty much most successful companies are punting a lot of this to the software and then trying to keep the hardware lean and mean. And then some of the hardware design is around all these other, issues about sparsity is really hard to deal with, right, at the compiler or software level because it's dynamic in some ways. And then picking the right bit width is very hard to deal with at the software level because maybe you need different bit widths at different times, these kinds of things. The mappings of trying to like keep things inside, storage structures, this is usually better suited to software than accelerators. Other questions? Yeah.
So like these code examples that you were showing, like,
Yeah.
are these the code that would be running on a single key, or is this like some kind of global? Because like this example walks through the entire convolution, right?
Right. So yeah, this is sort of like sort of into one piece. Like this is a serial piece of code,
Right.
right? Which means you have to walk through the whole convolution. In reality, this would be spread across. It would be parallelized across.
Right. So like what exactly would that look like? Because then in the MACD access pattern, we actually would only have like one wait or one output for the entire line.
So if you were output stationary, is that what you mean?
Or I mean, yeah, like any like the particular value that we're using, like has to be.
So let me go back to one blur because this one is kind of crazy looking, but like this, right? This is sort of well, let's go back to one that's not got the weird in this thing. So this is wait stationary. So what you're saying is that like basically if the processing is wait stationary, then that means that each PE basically loads one. No, this is not wait stationary. This is Is it? The R is moving, the weights are moving. This is output stationary. Why does it say wait stationary? Let me find a slide that's not broken. This is what's going on here. Okay, this is output stationary, right? Are we all in agreement now? This is wait stationary. Okay, so let's do wait stationary. So WR, that means that one PE has one WR in it, essentially. right? And so that means that that one PE is going to load in that right side of the multiplication, and it's going to live there, and then it's going to process everything to do with that right side of the multiplication, or everything to do with that inner loop, essentially, right? And then you could distribute this. Well, I mean, this is kind of simplistic, right? Because it sort of assumes, okay, so if I have a one convolution that I'm sort of putting it into an array, you'd have W0 be one element. So in this example, you would have R different PEs, okay? And then each PE would be responsible for one inner loop, and then it would pass its output to the next inner loop. And the way you keep them all active is just keep feeding the new activation. So they're each like doing a different thing, right? After they finish their inner loop. Does that make sense?
Yeah, so I mean, like in that case, like what would it, like in the code, what would it look like to say, I want to pass this value to the next PE? Like, would that be like we're stored with some special magic address?
There's no stores, right? There's no like decoder, there's no front end running a real ISA. All that stuff has float, right? So it would really just be like when you output, your output would, I mean, you need to have some control, right? Because you need to know whether you're going to accumulate or send essentially your output, right? So if I've got weight stationary, then let's go back to the picture. Let's output this, right? So here, I'm not actually accumulating anything locally. So my output is always going out to the next processing element. So you can envision this as like, there's maybe a buffer that goes to the interconnect, or it's a direct connection. Like if it's super aggressively timed, I guess you could have like one cycle, right? You sort of like put the bits on the output of the Mac, and then on the next cycle, though, you wire the outputs of that directly into the input, of the next Mac. It's pretty damn efficient, right? If you can time it all out correctly, there's no buffering, no storage in between. So you basically are always sending your output. Like your Mac's always going to this network. Now in reality, like if you want to send something on dock, there's probably a buffer, a couple cycles on a pipeline or something, right? But you don't need a special instruction, like it's only doing this instruction like over and over and over. Does that make sense?
So like we're saying that the output is implicitly like always.
Correct. There's never a reason for me to do anything with my output except send it to the next element.
In that case, like, so like the diagram we looked at before, that we had these things in the grid and they were all connected to each other.
Yeah.
Then like how
That's abstract, right? So the very first one, when I showed you like a general systolic like data flow, you can build it that way. But if you only use the connections in a particular pattern, there's no need for those connections. Right? So I mean, this is systolic. It's a very simple example, right? But even the MBDLA, right? It was systolic, but it wasn't like, remember there was a whole row that then flowed into the next row, because there was not really a need to share it this way. There'd only be a need to share it this way. So that diagram I showed you is not going to be taken literally, right? It's like you could literally have a sea of PEs. And that's sort of how Cerebrus does it too, because then it's a little bit more programmable, right? Because then you can decide which to flow it to. But now it's sort of like an FPGA kind of problem where you're trying to map like the flow of computation to the circuit. If you know that you've got particular patterns, you don't need a complete all-to-all sort of mesh topology. That makes sense. Good question. Other questions? Yeah.
There's no like later.
It depends. I mean, again, it depends. So for Cerebras, they do have an ISA. Like they have a very simple ISA for each PE. So you could, there are folks in like national labs, for example, who are buying these Cerebras machine learning accelerator things and then trying to retarget them at like fluid dynamics or bomb explosions or whatever, which means they are at some level programmable. They're not all programmable. Like MBDLA, you can't go into each PE and like tell it to go do a division or something, right? Like it doesn't have that kind of capability. And, you know, the question, there's always the question of like, well, like, where's the right balance between like having it be programmable, and having it not be programmable? Like this class is called Programmable Accelerator Architecture, so we're sort of ending off with this thing that's far, far less programmable. But that's sort of the trend, right? It's almost always also the trend in GPUs, because that's what the tensor core is. That's what the, you know, ray tracing unit is. They're like these sort of not super programmable elements that sort of get bolted onto this programmable machine. But this stuff usually isn't super programmable. If you look at these academic papers where they've got RTL, like each element doesn't run RISC-V, right? It runs like back and maybe load this value or something, right? There's like a small subset of things that do. Good question. Yeah.
So that to like launch your job, is it like space out program?
So, I mean, typically, like, look, all of these things need you, right? To like load the data in off a disk and like handle an operating system and all this other stuff, and you bolt it onto the CPU in some way, right? By PCIe or some specialized link or something. And then you could, from a programmer's perspective, like TPUs like this, you can go rent a TPU today. You can go and pay Google, whatever, and you can, you know, on the cloud service, they'll give you access to a TPU. For most machine learning people, they don't even know there's really a TPU because it's all buried behind PyTorch. Like you just have your PyTorch file and you say, go use TPU or go use GPU and just do it. Lower down, like in the system level, there's going to be some functions built into some driver layer libraries or something that will say like, okay, start initiating the PCIe transfer of this data, you know, special doorbells that say, I want you to load these weights that are at this location in memory into your array. Like similar to the way like, you can think of like an FPGA being programmed, right? FPGAs are programmed with like bit streams, right? You take your design and you like take your RTL and then you know, compile it down to netlist, and then eventually it becomes like a bunch of ones and zeros that then just get shoved across some internet to your FPGA that say whether each gate should be programmed on or off, or this connection should be made or whatever. It's sort of like that. And so there'll be some software layers in between that allow that kind of programmability. And there's a spectrum. I mean, this is sort of like one extreme, but typically the people who use these things never have to deal with any of this because it's buried behind the software layers. If you guys get jobs as like systems engineers at some of these companies, which is what, you know, some of you will, right? You'll have to deal with this kind of low level detail. Good question. Other questions? But it's not like you can run CUDA, right? It's not like you can like go write up your CUDA program and like spun like, no, you can't do that. That's the trade-off they've made. Unsuccessfully for the most part so far, right? Everyone still uses GPUs. Maybe someday, you know, that will change, or GPUs will change, the program model will change. But today, you know, if you want to use one of these specialized accelerators, you have to use some kind of libraries in between. Okay. Other questions? I'm 4 minutes over. I'm done with this slide set. We'll move on next week to some other sort of accelerators in this space. This first one is sort of meant to give you an overview of like, this is the landscape circa 2020 of different DNN accelerators, and we'll move into some more researchy type of things that people have been doing. Okay. Anything else? All right. Have a good Tuesday. Try not to be too sad about the basketball game. Or yeah, if you did, we're unaware Purdue lost, so if people seem sad today, if you're TAing and your undergrad seems sad, that's why. All right, sorry. Thank you all. See you Thursday.